Ionic bonding is a type of chemical bond that involves the electrostatic attraction between oppositely charged ions, and is the primary interaction occurring in ionic compounds. The ions are atoms that have lost one or more electrons and atoms that have gained one or more electrons. This transfer of electrons is known as electrovalence in contrast to covalence. In the simplest case, the cation is a metal atom and the anion is a non-metal atom, but these ions can be of a more complex nature, e.g., molecular ions like NH4+ or SO42-. In simpler words, an ionic bond is the transfer of electrons from a metal to a non-metal in order for both atoms to obtain a full valence shell. It is important to recognize that clean ionic bonding, in which one atom takes an electron from another, cannot exist. All ionic compounds have some degree of covalent bonding, or electron sharing. Thus, the term ionic bonding is given when the ionic character is greater than the covalent character, that is, a bond in which a large electronegativity difference exists between the two atoms, causing the bonding to be more polar than in covalent bonding where electrons are shared more equally. Bonds with partially ionic and partially covalent character are called polar covalent bonds. Ionic compounds conduct electricity when molten or in solution, but typically not as a solid. Ionic compounds generally have a high melting point, depending on the charge of the ions they consist of. The higher the charges, the stronger the cohesive forces and the higher the melting point. They also tend to be soluble in water. Here, the opposite trend roughly holds. The weaker the cohesive forces, the greater the solubility. Overview. Atoms that have an almost full or almost empty valence shells tend to be very reactive. Atoms that are strongly electronegative often only have one or two empty orbitals in their valence shell, and frequently bond with other molecules or gain electrons to form anions. Atoms that are weakly electronegative have relatively few valence electrons that can easily be shared with atoms that are strongly electronegative. As a result, weakly electronegative atoms tend to distort their electrons cloud and form cations. Formation. Ionic bonding can result from a redox reaction when atoms of an element, whose ionization energy is low, give some of their electrons to achieve a stable electron configuration. In doing so, cations are formed. The atom of another element, whose electron affinity is positive, then accepts the electron, again to attain a stable electron configuration. And after accepting electron, the atom becomes an anion. Typically, the stable electron configuration is one of the noble gases for elements in the s block and the p block, and particular stable electron configurations for d block and f block elements. The electrostatic attraction between the anions and cations leads to the formation of a solid with a crystallographic lattice in which the ions are stacked in an alternating fashion. In such a lattice, it is usually not possible to distinguish discrete molecular units, so that the compounds formed are not molecular in nature. However, the ions themselves can be complex and form molecular ions like the acetate anion or the ammonium cation. For example, common table salt is sodium chloride. When sodium and chlorine are combined, the sodium atoms each lose an electron, forming cations, and the chlorine atoms each gain an electron to form anions. These ions are then attracted to each other in a 1-to-1 ratio to form sodium chloride, Na plus Cl Na plus Cl minus NaCl. However, to maintain charge neutrality, strict ratios between anions and cations are observed so that ionic compounds, in general, obey the rules of stoichiometry despite not being molecular compounds. For compounds that are transitional to the alloys and possess mixed ionic and metallic bonding, this may not be the case anymore. Many sulfides, e.g., do form non-stoichiometric compounds. Many ionic compounds are referred to as salts, as they can also be formed by the neutralization reaction of an areneous base like NaOH with an areneous acid like hydrogen chloride NaOH plus hydrogen chloride NaCl plus H2O. The salt NaCl is then said to consist of the acid Cl- and the base Na+. The removal of electrons from the cation is endothermic, raising the system's overall energy. There may also be energy changes associated with breaking of existing bonds or the addition of more than one electron to form anions. However, the action of the anions accepting the cation's valence electrons and the subsequent attraction of the ions to each other releases energy and, thus, lowers the overall energy of the system. Ionic bonding will occur only if the overall energy change for the reaction is favorable. In general, the reaction is exothermic, but, e.g., the formation of mercuric oxide is endothermic. The charge of the resulting ions is a major factor in the strength of ionic bonding, e.g., a salt C plus A minus is held together by electrostatic forces roughly 4 times weaker than C2 plus A2 minus according to Coulomb's law, where C and A represent a generic cation and anion respectively. Of course, the sizes of the ions and the particular packing of the lattice are ignored in this simple argument. Structures. Ionic compounds in the solid state form lattice structures. The two principal factors in determining the form of the lattice are the relative charges of the ions and their relative sizes. Some structures are adopted by a number of compounds. For example, the structure of the rock salt sodium chloride is also adopted by many alkali halides and binary oxides such as MgO. Pauling's rules provide guidelines for predicting and rationalizing the crystal structures of ionic crystals' bond strength. For a solid crystalline ionic compound, the enthalpy change in forming the solid from gaseous ions is termed the lattice energy. The experimental value for the lattice energy can be determined using the Born-Haber cycle. It can also be calculated using the Born-Landé equation as the sum of the electrostatic potential energy, calculated by summing interactions between cations and anions, and a short-range repulsive potential energy term. The electrostatic potential can be expressed in terms of the interionic separation and a constant that takes account of the geometry of the crystal. The further away from the nucleus, the weaker the shield. The Born-Landé equation gives a reasonable fit to the lattice energy of, e.g., sodium chloride, where the calculated value is minus 756 kJ per mole, which compares to minus 787 kJ per mole using the Born-Haber cycle. Polarization effects. Ions in crystal lattices are purely ionic compounds are spherical. However, if the positive ion is small in, or highly charged, it will distort the electron cloud of the negative ion, an effect summarized in Fajon's rules. This polarization of the negative ion leads to a build-up of extra charge density between the two nuclei, i.e., to partial covalency. Larger negative ions are more easily polarized, but the effect is usually important only when positive ions with charges of 3+ are involved. However, 2+ ions or even 1+ show some polarizing power because their sizes are so small. Note that this is not the ionic polarization effect that refers to displacement of ions in the lattice due to the application of an electric field. Comparison with covalent bonding. In ionic bonding, the atoms are bound by attraction of opposite ions, whereas, in covalent bonding, atoms are bound by sharing electrons to attain stable electron configurations. In covalent bonding, the molecular geometry around each atom is determined by valence shell electron pair repulsion via CPR rules, whereas, in ionic materials, the geometry follows maximum packing rules. One could say that covalent bonding is more directional in the sense that the energy penalty for not adhering to the optimum bond angles is large, whereas ionic bonding has no such penalty. there are no shared electron pairs to repel each other, the ions should simply be packed as efficiently as possible. This often leads to much higher coordination numbers. In NaCl, each ion has 6 neighbors and all bond angles are 90 degrees. In CsCl the coordination number is 8. By comparison, carbon typically has a maximum of 4 neighbors. Purely ionic bonding cannot exist, as the proximity of the entities involved in the bonding allows some degree of sharing electron density between them. Therefore, all ionic bonding has some covalent character. Thus, bonding is considered ionic where the ionic character is greater than the covalent character. The larger the difference in electronegativity between the two types of atoms involved in the bonding, the more ionic it is. Bonds with partially ionic and partially covalent character are called polar covalent bonds. For example, NaCl and MgO interactions have a few percent covalency, while CO bonds are usually 50% ionic and 50% covalent. Pauling estimated that an electronegativity difference of 1.7 corresponds to 50% ionic character, so that a difference greater than 50% corresponds to O bond, which is predominantly ionic. Ionic character in covalent bonds can be directly measured for atoms having quadrupolar nuclei. These nuclei are generally objects of NQR nuclear quadrupole resonance and NMR nuclear magnetic resonance studies. Interactions between the nuclear quadrupole moments Q and the electric field gradients are characterized via the nuclear quadrupole coupling. Constants QCC equals E2QZZQ, where the EQZZ term corresponds to the principal component of the EFG tensor and E is the elementary charge. In turn, the electric field gradient opens the way to description of bonding modes in molecules when the QCC values are accurately determined by NMR or NQR methods. In general, when ionic bonding occurs in the solid state, it is not possible to talk about a single ionic bond between two individual atoms, because the cohesive forces that keep the lattice together are of a more collective nature. This is quite different in the case of covalent bonding, where we can often speak of a distinct bond localized between two particular atoms. However, even if ionic bonding is combined with some covalency, the result is not necessarily discrete bonds of a localized character. In such cases, the resulting bonding often requires description in terms of a band structure consisting of gigantic molecular orbitals spanning the entire crystal. Thus, the bonding in the solid often retains its collective rather than localized nature. When the difference in electronegativity is decreased, the bonding may then lead to a semiconductor, a semi-metal or eventually a metallic conductor with metallic bonding.